2.3, applied functions, variation. So you've seen direct variation before. It occurs when one quantity is a constant multiple of another. So we use the function form f of x equals kx to model this dependence. K cannot equal 0. And we say that y varies directly as x, or y is proportional to x. K is called the constant of proportionality. So it's really similar to slope-intercept form. The K is like your slope. And there's no y-intercept, it's b. So if you were to graph f of x equals kx, it would start at the origin, and it would go, depending if k is positive, it would go in an upward direction. And it would pass through 1 comma k. So here is an example. During a thunderstorm, you see the lightning before you hear the thunder, because light travels much faster than sound. The distance between you and the storm varies directly as the time interval between the lightning and the thunder. Okay, so in part A, suppose that the thunder from a storm 5,400 feet away takes 5 seconds to reach you. Determine the constant of proportionality and write the equation for the variation. Okay, so we are going to use the formula distance equals rate times time. So we are told the distance is 5,400 feet. And it takes 5 seconds. So time is 5. So we are in feet per second. So it asks us to find the constant of proportionality. In this case, the constant of proportionality is the rate. It's standard. It will stay the same. So we need to solve for r. So divide by 5 on both sides. And we got 1,080. And we're in feet per second. It's our rate, our constant of proportionality. So writing the equation for the variation, we now use a general d that we can plug in any distance to find the time, and d equals 10,080 t. Okay, part B asks to sketch the graph of this equation. What does the constant of proportionality represent? Okay, so we need the first quadrant only because k is positive. So t is on the horizontal axis, t for time, d for distance is on the vertical axis. Okay, so at time 1 in our equation is d equals 1080 t. If t equals 1, we get out 1080. t equals 2, we'll get out 2,160. And at time 0, we know it's 0. So, because there's no storm. So, we can use those 3 points and model our equation. And it's made by hand, so it's not the perfect graph, but it's pretty close. There we go. Okay. It also asks us what the constant of proportionality represents, which is this 1080. K represents the speed of sound. Part C asks if the time interval between the lightning and thunder is now 8 seconds, how far away is the storm? So we're going to use our equation, d equals 1080 t, and now we're being told t equals 8. So plug it in, distance equals 1080 times 8. So our distance is 8,640, and we are in feet, which is about a mile and a half away. You've also seen inverse variation before. It's the equation f of x equals k over x. X is in the denominator, that's what makes it inverse. K is our constant and it cannot be equal to 0. It is said that y is inversely proportional to x, or y varies inversely as x. So if we were to graph a general inverse variation equation, y equals k to the x, and this is for when k is greater than 0, so it's positive, it will look as such. It's going to be a curve in quadrant 1. It will also be symmetrical to the origin, so it will flip and be mirrored across. So it's a hyperbola with its 2 branches in opposite quadrants. Another type of variation is called joint variation. Forgot the T. A physical quantity often depends on more than one other quantity. If one quantity is proportional to 2 or more other quantities, we call this relationship a joint variation. So there's more than 2 variables. In the quantities x, y, and z, if the quantities x, y, and z are related by the equation z equals kxy, where k is a non-zero constant, we say that z varies jointly as x and y, or z is jointly proportional to x and y, because it depends on what x and y are. It can also be used with inverse variation. We could have it arranged so that z equals k, which is our constant. K is our constant in all of these. So z equals kx over y. And how you would say this is z is proportional to x, because it's in the numerator, and inversely proportional to y. inversely proportional to y because it's in the denominator. An example using joint variation is Newton's law of gravitation, which says that two objects with masses m1 and m2 attract each other with the force F that is jointly proportional to their masses and inversely proportional to the square of their distance r between the objects. Okay, so we're going to express Newton's law of gravitation as an equation. Alright, so first thing says that two objects with masses m1 and m2 attract each other with a force F that is jointly proportional. So m1 and m2 are jointly proportional. So that means they are multiplying. And it's inversely proportional to the square of the distance r between the objects. So r is getting squared, and because it's inversely proportional, it's in the denominator. We also have to have its constant, and in Newton's law of gravitation, its constant is a capital G, so it's multiplying by G. So this is our equation for force. So force equals G times m1 times m2 over r squared.